to a new session. So in our last session we had a brief introduction to the heap, and now we know that heap is a kind of binary tree, special binary tree, like we had the binary search tree, for example. In binary search tree we were checking every node according to its children, like every node should be greater than the left child and smaller than the right child. That was the binary search tree. And heap is also a kind of binary tree. And in the heap, so you should know that we have max heap and min heap. So if every node is greater than or equal to its children, that is a max heap. Or if every node is smaller or equal to the children, that is a min heap. For example, let's check these two examples side by side. In the max heap, every node is bigger than the children. For example, this one bigger than this two, this one bigger than this two, this one bigger than this two. Now in the min heap, every node is smaller than the children. This one is smaller than the children. This one is smaller than the children. This one is smaller than the children. If any binary tree has this property, that is heap. And it is min heap or max heap based on how it is sorted. So, and also you should know that whenever you add new element, new node in your heap binary tree, you always add at the end of your binary tree. And by that you mean that if you consider it level by level, you fill every level from the leftmost side. So, and now you know that how to represent a heap into an array, because once you represent a binary tree in the array, now it's very easy for you to work with an array. You just need to know how to work with an array. That means simply you're working with the heap or binary tree. And there is a established relationship between all the nodes, between children and parent. For example, we said for any given index in the array, once we represent the heap in the array, so you know that the array is zero based index. That means it starts from 0, 1, 2, 3 and up to the last one. So now for any index, the left child is at 2i plus 1. The right child is at 2i plus 2. The parent is at i minus 1 over 2. For example, let's see this node. So now see its parent. Its parent is 100. So now first see the index of this node in the array. 0, 1. So this index is 1. Now the left child, 2i, that means 2 times 1 plus 1. So it is 2 times 1, 2, 2 plus 1, 3. The left child should be at index 3. So the left child, this number 10, should be at index 3. Now let's see. 0, 1, 2, 3. Yes. The right child should be at 2i plus 2. So I was 1. 2 times 1, 2. 2 plus 2, 4. The right child, this 15, should be at the index 4. Now let's see. 0, 1, 2, 3, 4. Yes. And the parent, 100. So now let's check that. Parent should be at I is 1, 1 minus 1, 0, 0 divided by 2, that means 0. So that means the parent should be at index 0. And now let's see, 100 is at index 0. So now we know that those relationships are established when we represent a heap into an array. So now that you know that we can represent a heap into an array, so now let's work all our examples within using an array. So okay, so now let's create a function how to insert a new node. Public void insert init value. So simply you can create an array list. For example, list, here the value of all these nodes are integer. List of, for example, let's give it the name heap equals new array list. Okay, So now that we have our array list here, so we can easily add all our nodes to this heap. So how we do that? You should know how to work with an array list. Array list has some built-in function. You can use them and easily add your new node at the end of the array. So you know that when you add at the end of the array, that means in the binary tree is filled level by level, and when you fill a new level, you start from the most left side. For example, the new node that you insert, that should be the left child of number 10. And of course, when you represent this within the array, there is no gap in the elements. So just use the built-in methods of the array list and add the new node at the end of the array. Just say heap dot add value. That's it. So now let's suppose we want to add a new node, let's say like 110. So I added this at the end. Now let me add this. $110. Okay. So I added this one like this. When I say heap.add value, so at first we added this method add new element to the end of the array like this, 110. So, but now see, it broke the property of a heap. Now you don't see that property that every child should be smaller than its parent because it's a max heap. So now the main process starts. How to heapify this? By heapifying means how to bring back the heap property in this. So that means you need to swap this new inserted element with its parent. When you bring that here, again you see that still that property is not brought back. Then you have to swap this here, and still you see it is 110 and it is 100, and again you need to swap this. After like all these swaps, you see that you bring this biggest node in the root position. Now you see that the property of every node is greater than its children is brought back. So now how can we do that? So now let's work with this array and move this 110 from here to this location. So first let's get the index of this new inserted element. Init, let's say current index equals. So you can easily get the length of this array, and that is heap dot size. So when you say heap dot size, it returns the length of the array. But you know that the array is zero-based index. We need to access the index of this new element. For example, there is 1, 2, 3, 4, 5, 6, 7, 8 elements, but the index here is 7, and we need that index. So I say minus 1. Okay. Now I have the index of this last inserted element. So I need to swap this with its previous one. And here I already defined as a method to swap, because every time we need this. And also I defined how to get the parent, how to get the left child, how to get the right child. That is exactly this relation. For example, I said when you get the parent, calculate that based on this formula. I minus 1 divided by 2. Return that. I means the index. And when you get the left child, exactly this formula. Right child, this formula. And when you swap, so of course when you swap these two, for example, how you can do that? first you need to create a temporary variable to keep one of them in the temporary variable, and then put this inside this node, and now you can get the value from temporary variable and put that here. So that is exactly happening here. So now let's check. 110 is inserted here now, but we need to swap it with its parent, and now we have the index also. So we need to continue this process until that heap property is brought back. That means every node should be greater than or equal to its children. So we say while the current index is greater than 0, as far as this, for example 110, is not in this location, we need to check it if it is if it has the heap property or not. So as far as it is greater than 0, and so as far as it is greater than 0, that means still it is not at this index, and it is smaller than the parent, or it is bigger than the parent, that means we need to swap that. As far as this index is not in this position, and this is bigger than its parent, or the parent is smaller than this one, that means we need to swap that. So I say that as far as the current index is greater than 0 and parent is smaller than this node, so I'm saying that get the parent, heap dot get. So how can we get the parent? So simply we need to call this method parent, call parent method, and pass the index. The index is current index. Okay. So get the parent, and we call this method just to get parent. Instead of writing this formula here, I can write this directly, this formula here also, that get the parent calculating this one, but writing this method is much cleaner code. So get the parent, and then check if the parent is smaller than this index, a heap dot get the current index. So let me have some more space here. Okay. Now, so what did we do here? What did we say here? We said as far as this new inserted element, as far as this one has not reached to the first position, that means still there's a chance that it is bigger than some nodes here. But when it comes to the index 0, that means it is in the root position, and there is no other parent, so that is the last one. But as far as it is not here, that means there is a chance that it is bigger than some other nodes. So we say as far as it is greater than 0 and the parent of this new inserted node is smaller than this one. So how can we get parent? So we get parent based on this formula. So we say heap dot get parent. So we pass the index of this node, and that was here in the current index. So we get parent like that. And we say as far as this parent is smaller than this new inserted node, heap dot get current index. So as far as these two condition meets, we need to swap them. That means we need to bring 110 here and 10 here. So at the first time this condition meets. Now the current index, it is greater than 0, and this parent is smaller than the current inserted node. So we say swap this, swap this one, current index with its parent. So to the parent we just pass the index of this node, and the index of this node is current node index, current index. Okay. Now we pass both indices to the swap method, and the swap method do the swap operations. See here, the two indices are given, and it creates a temporary variable. First put one of the node in that temporary variable, and then set the values into their right positions. So as far as this condition meets, we need to swap that every time. And so right now when we swap this, this happens. Number 10 comes here, and number 110 comes here, like this. So this swap happens. And when we do that swap, so we need to update the index of this new inserted node. So we say current index equals parent. So now, right now, current index still it is not updated, so this means it is here. It is here at this position. So, but when we update this, that means we need to get in the parent, the index of its parent, and right now the parent is also the new inserted node. So I just call the method parent and pass the current index. That means it is here still. Current index. Okay. Now, when it returns the index of its parent, that means now it is the new inserted element. So that means the current index is updated. So, and also number 10, 110 comes here. It gets replaced with this one. So 110, 10, like this. So again, it checks, is still the current index greater than 0? Yes, it is greater than 0. And does this condition meet? So get the parent. Okay, we get the parent that is 40. Is the parent smaller than the current index? Again, we see it is smaller. Then we swap that again. So when we swap that, this happens. 110 comes here. 40 comes here. That means 110, 40. That happens like this. So again, we need to update the current index, the index of this one also. So we say current index, it was here, but after this time, the index of its parent becomes the index of new node, which the new node has already moved here. So again, we check, is the current greater than 0? Yes, it is greater than 0. So if it is greater than 0, and is it smaller than the parent? We get the parent, and again it is that. So again we need to swap that. So we bring the 110 here, and 100 here, 100 here. We swap that, and we update the index also. So now when it comes to check this time, is the current index greater than 0? So we updated the current index, it is 0. So that means this condition does not meet anymore. And that means the binary tree has the property of heap. Now here is a heap. Now if you check, every node is greater than or equal to its children. See? So it was how you inserted a new node. Now let's see how we delete a node from the heap. So public, so most of the time when you delete a node, you need to return that. So, and the type of all of these are like integers in the array. Also you see that. So I give it integer, public integer delete. Okay. Let's return an integer for the moment, just not to see that error. That doesn't give a good feeling. Okay. So when you delete, you always delete from the root. That is one of the reasons that we use heap in binary in the priority queue, because you know that queue always removes from the first, and heap already has a priority. It is sorted based on a priority. By priority I mean either it is a max heap or min heap. Sometimes you give like the higher number the higher priority, sometimes you give the smaller number the higher priority. So in any way, always you remove the root node first. So for example, when you remove 110, what happens next? That is the main question that you should ask. Let's imagine you remove this 110 from here. If like when you see it, this, if you take it out, the tree fall apart, but it should not happen like that. So always remove the root element, replace the root with the last element in the heap, and the last element in the heap is number 10. In the picture also you see. So you remove 110 from here and you replace that with number 10. You bring back number 10 here. So now let's suppose you remove this 100, you remove that and you brought number 10 there. Like this. And in the array also you removed 110. I didn't. So earlier I had to bring that, I had to brought that here, but I forgot to do that. This is not a problem. So let's say you removed 110 from the head, and when you remove that, so you replace that with 10 from the last, like this. But now, do you see the heap property here? No. Now you see that this one is smaller than the children, but these nodes are bigger than the children. So that means you don't have the heap property here. And that is when your heapify process starts. That means now you deleted the root node, but you need to heapify this. That means you bring back the property of heap on this property, on this binary tree. So almost similar to insertion, that you needed to swap with its parent. Now you need to compare this with its children and swap with the children. So that is when the main process starts. So before you do anything, you always check if the uh, array should not be empty, because if it is empty, like, you don't need any operation, just return and finish the method. Return the message and say it is empty, and that's it. So you say if heap dot is empty, if it is true, throw new illegal state exception and say heap is empty. That's it. You don't need to do anything else. But if it is not empty, if it is like this, then you need to do all those operations. So I will do that faster without much explanation, because you already know what is our goal. In order just to take it less time, I will write this faster. Okay. So now let me have the max value here. Heap dot get index 0 last index equals heap dot size -1. Now heap dot set 0 index with heap dot get dot last, heap dot get last index, and heap dot remove last index. Okay, so now you remove that. Init current index equals 0. Now let's say while left child of current index is smaller than the heap dot size, you say init child index equals left child current index. So now say if right child current index is smaller than heap dot size, and heap dot get right child pass the current index. If it is greater than heap dot get greater than the child, then we need to set the child index to right child of current index. Okay, and if heap dot get current index is greater than or equal to heap dot get child index, if it meets this condition, then we need to break. Otherwise, we need to swap current index with the child index. That's it. And update the current index equals to child index. So at the end, return the max value. Okay, this was the whole process. I did not explain this in details because it was taking much time, so I just wrote the code much faster, and now you know all the process, what to do. I hope it was useful for you. So you process all the swapping, and until the end you bring back the heap property. Until the next lesson, wish you all success, and if you have any questions you can ask me, specifically about the delete, because the video is becoming so much lengthy. It is already lengthy, but still I hope you can listen to all of them and ask your questions in the comment box. Have a nice time, everyone.